Alright, so in this video we're going to start talking about molecular orbital theory and what that is, and what that means, and how we use that to talk about atoms and molecules and bonding and so on and so forth. Okay? So, right, the main thing in molecular orbital theory is that we're approximating the wave functions of molecules as combinations of atomic orbitals on atoms, right? So the idea here, right, is that, right, I have some total wave function, right, that is going to be equal some combination of psi1 plus psi2, for example, right? That you know, these are my molecular orbitals, and I'm taking combinations of my atomic orbitals, right, to make them. Okay. So we'll start with the simplest case of H2 plus, right? And this is the simplest case because it has one electron, right? So the reason it's so simple is because it just has one electron, so one could solve this exactly, right? But we're going to use molecular orbital theory instead, right, to get the same type of answer if you were to try to solve this differential equation exactly like we did for the hydrogen atom. So in molecular orbital theory, right, what we're going to do is we're going to assume that, right, some wave function, some atomic orbital, right, or some molecular orbital, right, this is my MO, right, my molecular orbital is a combination of these atomic orbitals that are located on atom A and atom B, right? So imagine we have H and H, right, and I'm calling this hydrogen A and hydrogen B, right? So 1sa is the 1s orbital on atom A, and 1sb is the 1s orbital on atom B, okay? And then here I'm taking the plus combination, right? And this is what we'll see ends up being the bonding type orbitals that we get, okay? And we'll kind of see that in the next slide, right? But if I want to look at what is the probability distribution, right, of the electrons in this bonding type orbitals, I'm going to call it, right, these plus orbitals, right, I take psi star psi, right, which is then you got to factor out this product rate, and then you're going to have, right, that probability density of atomic orbital on atom A, right, and then you have the same thing on atom B, and then you have this extra term here, right, through this linear combination where you've added some extra probability density that's related with the product of 1sa times 1sb. And so how that works is we kind of have this picture here on the right, okay? You have, right up top in the shaded region is sort of the, you know, the density, right, for 1sa, and this is 1sb, right? So the, you know, or kind of colored in, right, that's sort of the density of just atom A, atom B being independent of each other, right? And then we have, right, this region in here where they overlap with each other, right? So that I get some increased density, right? So the purple lines down here, right, is the 1sa density and the 1sb density. The blue line, right, that blue line, right, corresponds to, right, psi plus star psi, right? So that's psi plus star psi, right, is that blue line. And we see that we have an increased density between these two atoms, right, because of this constructive interference, as it's called, with psi 1sa and psi 1sb, okay? And this enhanced overlap of these wave functions between the atoms, right, gives you an increased electron density between the two nuclei, which is why we consider these a bonding type orbital, right? Because imagine if I have two atoms bonding with each other, right, they will be bonding only if they're sharing electrons between each other. And if they're sharing electrons between each other, I should get a bunch of electron density in between those two atoms, right? If they're not really sharing their electrons, there shouldn't be any increased electron density between the atoms, right? So this gives us our kind of covalent type bonding, right? And this is our bonding orbital, right? And so kind of just plotting this in another way, in kind of a three-dimensional plot here is again just the same information as the previous slide, right? Where we have psi plus is this sigma bonding orbital that we often think of, right? And then we talked previously about electron configurations, right? And then the idea here is then the electron configuration for H2 plus is just that right there, right? Because it's just literally putting an electron in the, the sigma bonding orbital. Okay, and we're going to call, right? So we're going to actually call psi plus is actually equal to psi sigma, right? This sigma bonding orbital. Right, now that we've established these are bonding orbitals and things like that, we're going to use the actual names we typically use of sigma bonding and anti-bonding. So the anti-bonding orbital is going to be related to the psi minus, right? So the psi minus here, right? This is this is going to be your sigma star, right? Your anti-bonding orbital, right? That's going to be your sigma star, right? And we see this is going to be an anti-bonding orbital because of this term here, right? In the bonding orbital, there is a plus here. In the anti-bonding orbital, this is a minus. That means I'm removing some electron density in this region where the two things overlap, right? And so we see drawn here, right, kind of indicating the phase. This has a positive phase, right? This is a negative phase, right? So you got kind of phase here, right? And then you got your positive phase here, right? So when they interact with each other, they're going to cancel with each other, right? So that again, in this blue curve here, right, I'm having my psi sigma star, right? This is my anti-bonding orbital. This is my minus orbital, okay? Right, and again, this is considered an anti-bonding orbital because I now have a decrease in electron density between the two nuclei, right? Essentially, there's a point where there's 0 electron density between the two nuclei. There's a node that's been put in these orbitals, right? So it's decreased electron density. Okay, and again here, just plotting these anti-bonding looking orbitals, right? In kind of a three-dimensional plot, just to get an idea, again, of what this kind of looks like, right? And again, we now have a node between the atoms, and right, this is considered anti-bonding, right? Because now you've done something even worse than just non-bonding, right? If you were non-bonding, right, there would not be any nodes between these electrons. You know, there'd be some overlap and things like that, but there wouldn't be electrons being shared between the atoms and such, right? But an anti-bonding orbital means that they actually forced the electron density away from being in between the two atoms, right? So this is sort of even worse, right? I have like my bonding orbital, my anti-bonding orbital, and then here I could have like a non-bonding orbital, right? I could consider some orbital non-bonding, right? It's kind of in between where it's just, you know, psi 1s, psi 2s or something, right? Like it's not a linear combination of the two, it's just a product of, say, the two. It would be sort of your non-bonding type orbital case, right? And so again, these anti-bonding orbitals is even worse than just if there's no bonding whatsoever. Worse in terms of energy, I should say. All right, and so kind of note, right, I just kind of drew that energy ordering, okay, that the energy difference between the non-bonded orbital here, right, these are your non-bonded orbitals, right, your non-bonded orbitals, right, the energy difference is always going to be smaller between your non-bonded orbital and the bonding orbital than it is the non-bonded orbital and the anti-bonding orbital, okay, right, and so what that means is I'm never going to have this electron configuration where I have, say, like, let's do, you know, 1 sigma 2, 1 sigma star 2, right? Where I put 2 electrons in the bonding, 2 electrons in the anti-bonding orbital, right? This is always going to be in higher energy than just having things not bonded whatsoever, right? So this is why, for example, helium-2 doesn't exist, because helium-2 would have that electron configuration, and that's higher in energy than just having, right, the 2 1s2s, right, having the 2 separate heliums, right, with each having 2 electrons in their 1s orbitals, right? So this is lower in energy than what's on the left here, right? The 1s2, right, the 2 1s2 occupations is lower in energy than the 1 sigma 2, 1 sigma star 2 electron configuration, okay? And so it's never going to be favorable to doubly occupy antibonding orbitals if I'm also occupying the bonding orbital. I'd rather just not bond anything whatsoever, okay? And this also kind of makes some sense for the fact, right, because I've added an extra node in my wave function, right, in the antibonding orbital, should be in higher energy, right, because as we talked about before, increasing the number of nodes in your wave function increases the curvature of that wave function, which thus increases the kinetic energy of that wave function, of that orbital. So these antibonding orbitals are high kinetic energy orbitals, so electrons that occupy those orbitals have very high kinetic energy, so they're very high energies, right, and it's not a very stable, not very favorable orbital to occupy. Okay. And just final note to kind of wrap up this introductory to molecular orbital theory, right? Just talk about the fact that often we use these terms Gorod and Ungerod. I'm going to say that right, you know, but we often use those terms, right, to indicate certain symmetry. So Gorod symmetry, G, means that if I invert my system, take something from this point, put in this point, it's the same sign, right? Ungerod is I have something that's positive, it then goes to negative when I invert it through the origin, okay? And so your bonding orbitals are going to have Gorod, your sigma bonding orbitals have Gorod symmetry, your sigma anti-bonding orbitals have Ungerod symmetry, right? So sigma G is kind of what we've been calling the sigma orbitals, and sigma U is our sigma star orbitals, okay? All right, so that's going to do it for kind of this introduction to molecular orbital theory. And next, we'll talk about molecular orbital theories in more details for different diatomic molecules beyond H2.